Welcome back to discussion of this different distribution of the wind speed. So, which are we talked about the um, normal distribution of the Gaussian distribution, as you can see here, where you can use this probability density function, and then you can estimate this. So, as I have emphasized that these distributions of the wind speed is very important to estimate the power and all this. The second one that we can talk about is that Weibull distribution. This is another kind of distribution. So there are different kinds of distribution which are possible. Um, but wind energy calculation, which we have also seen earlier, very commonly use this Weibull distribution. Okay, so this distribution has one is the scale parameter of C, and another is the shape parameter or factor, which is kappa. So this we have already seen that while talking about the Weibull distribution. Um, so here that f of u is represented as 1 minus exponential minus u by c to the power k. So my pu would be f of u prime. So one can write k by c, u by c k minus 1 into exponential minus u by c to the power k. So it's taking the derivative of that. So you can get this. So what you can show that the mean and very compared from this C and K using the gamma function. So we can use the gamma function. So gamma of x is 0 to infinity minus t to the power dt, where gamma of n is defined as n minus 1 factorial. So gamma 1 is 1, gamma 2 is 1 dot so like that. So using this gamma function and this we can estimate the mean wind speed. So that can be u c into gamma of 1 plus 1 by k. And my variance would be c square gamma 1 plus 2 by k minus c square gamma 1 plus 1 by k whole square. So this you can write 0 to infinity u square pu du minus u bar square. So one can write 0 to infinity u minus u bar square probability of u into du. So that's how the variance is calculated. So if you look at the variation of the gamma function with respect to k, this is how this varies. So let's say 3, this is 1, this is gamma 1 plus 1 by k. Okay. And this is something 0.88. This would be 1. This is the variation of the gamma function. Okay. So if you have a, this is my power curve. and can go like this. So this could be cut-in speed. Cut-in speed. So this is cut-out speed, and this is designed wind speed. Designed wind speed. This is for a given turbine, which is fixed area for that. So this is how the power curves would look like. Now you can have another kind of distribution. So these are different distributions which are possible. This is Rayleigh distribution. Okay. So this is a special case of Weibull distribution with kappa equals to 2. Here gamma 1 plus 1 by 2 is root over pi by 4, and C is u bar root over pi by 4. So here you have f of u 1 minus exponential u by c square, and you have p of u 2 by c square u exponential minus u by c square. So this a Rayleigh distribution is a special case of Weibull distribution with kappa equals to 2. So Rayleigh distribution corresponds to vector magnitude of two-dimensional Gaussian distribution. So this one can say this corresponds to vector magnitude of 2D Gaussian distribution. Okay. So these are different kind of distribution that you can have. So obviously we had the simple one, which is of the normal distribution of Gaussian distribution. We had then Weibull distribution, which we have talked enough because for different site, and this is commonly used in the wind energy calculations. Then you can have the Rayleigh distribution, which is again a special case of the Weibull distribution and things like that. So these are, I mean, one can now talk about some kind of an thing. Let's say, given a wind speed and power curve, one can estimate what is the, let's say, given is the wind speed distribution and power curve distribution. So these are the things which are given. So one can find out the average power. So average power per year. So let's say average power per year, which could be P average, is P into du. So that's how, obviously some distributions which should have been given, And once you have the distribution, then you can easily estimate uh, the average power carbon uh, that thing. So now what we can look at the some spectral properties of wind or statistical properties of wind. So let's say some spectral properties of wind. Okay. So here what we can have, let's say if your wind speed variation is there, which is some kind of an, then you can find out autocorrelation and PSD. So which is PSD is nothing but power spectral density. If a Fourier series is taken, then the spectral density is obtained. It often kind of an, let's say, if you take a Fourier series, and then this is the frequency, then it will look like that. So this is f into s of f. Here s of f is the PSD, power spectral density. This is an example of Fourier series. Uh, and so this is your, you can say this is my synoptic peak weather system variation. This say that Delhi peak. This is called the spectral gap. Okay, it could be 2 hours to 10 minutes. This is 1 second. This could be, it's less than 10 minutes. This is, let's say, 24 hours. This is kind of a year. So this is a density is a Fourier transform. So this is how. What happens is that the turbulence happened at time scale which is very small, or sampling time scale could be 10 minutes or so. Turbulence intensity, one can, turbulent intensity can be defined as variation by U bar, where U bar is mean over 10 minutes. Sigma U is a standard deviation. Then what we can say that U bar is 1 by n summation of I equals to 1 to n ui, and you can write sigma square 1 by n minus 1 summation of I 1 to n ui minus u by square. This is how you can estimate these things. So another interesting quality is the autocorrelation. So this autocorrelation is auto. correlation. So this is a method of finding repeating pattern, such as periodic wind patterns. In case of wind, it is looking for dependence of wind on conditions of the previous instant of time. So the autocorrelation function, which is let's say RT delta, one can estimate, let's say R delta 1 by sigma square n minus R 1 to n minus R ui minus u bar square ui plus R minus u bar. Here the delta t is sampling time, R is the lag number, and R delta t is the lag time. So if you can plot that, let's say t autocorrelation function. So this is t. This is let's say integral time scale of t. This is my RT autocorrelation, and this is 1. So this graph shows that wind is strongly autocorrelated at a very short lag time, not so strongly at longer lag time. So this shows that strong correlation at very short time, but not so strongly correlated longer lag time. This is kind of expected because we expect wind 1 second ago to have a big influence on the current wind, while not so much for the wind from a day ago. So that means in a smaller scale, you would expect more variation and more influence on the wind speed variation, whereas uh, you do not expect that the impact would be too high from previous day or day before that, or maybe few days before. So short times variations would be strongly correlated, which clearly you can see from here. But for a longer duration, effect should be as less as possible. That's how the wind characteristics is all about. Okay. Now, from here, one can estimate integral length scale. So you can estimate integral scale, which is L, it U bar into T. So this is kind of approximation size of turbulent interruption. This is what you can find out from these different correlations and all these things. What now we can see, so that gives you an idea about how these things are correlated and not. So what we want to look at it again, go back to this. So these are kind of looking into the distributions, and then from there getting the correlations and the integral scale calculations. So what we would like to now talk about and look at the effect of the surface temperature and how the atmospheric labs actually play a role. So obviously, we need to see how temperature variation takes place of the surface. Okay, so we can quickly look at atmospheric density and pressure. Okay, these are important aspect because this going to be because wind power is a function of air density because we know this density. So one hand we talk about wind power, which is also variation with the density, and then density is variation. Density is also kind of a function of pressure and temperature. And temperature again is function of height. So there is an interconnectivity. Essentially, wind power. This is wind power, which becomes inherently function of pressure and temperature. Now, if you assume that ideal gas law, ideal gas law, then the density and pressure variation can be estimated like that. Or I can say density is P by RT, which is kind of a 3.4837 P by T. Okay. So you can get that thing where the units are P is in Pascal, Kelvin. So that's how you can get that. So the international standard atmosphere assume that the sea level temperature and pressure. So if you look at sea level, the pressure would be 101.325 kPa and temperature is 288.15 Kelvin. And obviously from here you can get sea level density is 1.225 kg per meter cube. So air pressure decreases with elevation above sea level. Up to 5,000 meter elevation, the pressure, so let's say up to 5,000 meter elevation, the pressure variation is like that 101.29, 0.011837 into height plus 4.793 into 10 to the 1 minus 7 z square. So here there is the elevation in meter and pressure that we will get here in kPa. Of course, the actual pressure may vary about to the standard pressure as weather pattern changes. Usually in practice at any given location, the daily and seasonal temperature fluctuations have a much greater effect on air density than do daily or seasonal change in pressure and air moisture. So that importance issue is that so one can, with the height, you can actually get this pressure, temperature, and all these things. Now there is a stability of atmospheric boundary layer. This is very, very important. We just talked about that some conditions, the boundary layer could be stable at some point of time, it could be unstable, and the stability is an important factor. The particular importance characteristics of the atmosphere is the stability. So here it tries to resist the vertical motion or to support existing turbulence. So the stability of ABL is a determining factor for the wind speed gradient. So this is an determining factors for wind speed gradients. That is essentially one can think about wind shear. So which are experienced in the first few hundred meters above the ground. So because you have a particular layer, boundary layer, which is there. Atmospheric stability is usually classified as stable, neutral stable, or unstable, that we have already seen. And the stability of Earth's atmosphere is governed by this vertical temperature distribution, which will result from the radiative heating or cooling of its surface. So this could be stable, neutrally stable, or unstable. And this is connected with the obviously the temperature distributions of the surface, which is again directly connected with the radiative heating or cooling and subsequent convective mixing of the air adjacent to the surface. So now we can see how these things changes. So the thing that we can look at is the lapse rate. So the lapse rate of the atmosphere is as the rate of change of temperature. I mean, this is rate of change of temperature with height. So that is what the Laplace is. So one can easily determine the lapse rate by considering the change in pressure with height and obviously using conventional thermodynamic relationship. Now, if the atmosphere is approximated as a dry, no water vapor in the mixture, so you assume the atmosphere to be dry, then ideal gas relations would, be applicable. And what we can write is that the dP is a change in pressure is rho g dz, where P is atmospheric pressure, rho is atmospheric density, Z is elevation above ground, G is local gravitational acceleration. So you can assume constant here, you can constant here. This negative sign here, this is coming because of the convention that height is measured positively upward. So since we are going above the height, that's what P decreases with the height. So what we can write from the first law of thermodynamics for an ideal gas closed system of unit mass undergoing a quasi-static change of state, that we can write that d of q equals to d of u plus p of dv, which is one can write dh minus vdp equals to cp dt minus 1 by rho dp. Okay. So this is what you can write, and we can use this and connect with the pressure variation with the height, we'll try to find out the lapse rate, which is kind of going to give you an idea about the condition of the atmospheric boundary layer, which is stable, neutrally stable, or unstable. Because that, on the other hand, allows to calculate wind shear. That wind shear is an important factor to be considered during design calculation. Okay, we'll stop the discussion here.